Hey everyone, this is Dr. Walker. This is video 252 called Torque on a Current Loop. I'd like to start off this video with a question. How is this possible? The brush head rotates when turned on. So what do you think causes this brush head to rotate? Any thoughts? Please put it in the comments below. Let's start off this video with the concept, torque on a current loop. We just learned in a previous video that if you have a wire, let's just look at one part of this loop here. If you have a wire that has a current and it's within an external field, it will experience a force. So it turns out that if you have a loop of wire carrying a current, then that force will actually cause it to rotate. Let's take a look at how this works. Let's consider, for instance, the right-hand side of this wire and use the right-hand rule to figure out the direction of the force on the right-hand side of this loop. The current is going upward, and then the magnetic field is the blue lines here coming kind of out of the page to the right. And so the force is into the page, which is called F back in this picture. If you do the same thing for the front wire with the current going down this way, and then folding out of the page towards you, then the thumb goes towards you as well. That's the front. Okay? So hopefully you're trying this out with me so that you can, see what I'm doing and see how it corresponds to the picture. So if you have these two forces, I've got a little loop here. If you have these two forces, I'll just put my loop like this, and there I am. And you're pulling with this F back and F front, so I'm pulling outward from this loop, right? There's no rotation there. I can pull as hard as I want. I might just break this thing in half, but it's not going to cause any rotation. However, you also have a force on the top part and the bottom part. So if you follow the same process, for instance over here with the current going to the left here, and so going to the left and then folding out of the page towards you, that the magnetic field, the thumb is up. So there's an upward force on the top wire with a similar process. There's a downward force on the bottom wire since the current is going in the opposite direction. So if you go back to your loop here, then all dark here, there we go. If you have an upward force and a downward force, you can see that the upward force will cause it to go this way and the downward force will push it down, and it will rotate this way. So I encourage you to try it out, but it will rotate because of the upward force and the downward force on these sides. So that's the concept behind the torque on a current loop. We learned in Physics 1 that when you have a force that causes a rotation, then that's a torque. Okay, so now that we know the concept that there's a current in a loop in an external field, that loop will rotate. Now we can get the equation for the torque. And I'm not going to derive it in this video, but if you want a decently difficult exercise, you can definitely try it on your own, but it comes from definition of torque being force times distance, where the force is perpendicular to the object being rotated. So this is the expression for the torque on a current carrying loop. The torque, tau, is equal to N, which is the number of loops, I is the current, A is the area of the loop, B is the external magnetic field, and theta, as you can see, is the angle right here. And I have a note for this. Theta is the angle between the magnetic field and the normal to the loop. So this is really important because a common mistake is thinking that theta is the angle between the loop and the magnetic field. But no, it's the angle between the normal to the loop. So the normal to the loop is this orange line here. Normal means it's perpendicular to the loop. So whenever you have a loop, you want to draw the normal to the loop. And then theta is the angle between the normal and the magnetic field. So it's really important to get the right angle when plugging it into this equation to get the torque on this loop. Let's go ahead and do an example. So maximum torque on a coil, this will be a plug and chug. We're looking for the maximum torque. We have 100 turn square loop, so that's N is the number of turns, or the number of loops, same thing, turns or loops, same thing. 10 centimeters on a side, so it's a square loop. So we know the area is length times width, so 0.1 times 0.1, since 10 centimeters is 0.1 meters. So that's going to give us 0.01 meters squared for the area. And then we have the current of 15 amps. I is 15 amps. And it's in an external field of 2 teslas, so B is 2 teslas. So we just learned the equation that torque equals NIAB sine theta. We're looking for the maximum torque. So like in the previous video, when you're looking for a maximum quantity, that means sine of theta is going to be 1, since that's the maximum possible value of sine of theta. So the maximum torque is simply going to be NIAB. And then we can plug in all of our givens. 100 times 15 times 0.01 times 2. And that's going to give us 30 Newton meters. If you remember, the unit for torque is force times distance. Alright, so that is it for this video. We're going to have a second part of this video where we will do an application and look at the electric motor.